Okay, the next topic that we're going to discuss is renormalized perturbation theory. And renormalized perturbation theory is just a nice way to organize the calculations that we've been doing so far. So it's not really something new, it's just a way of organizing what we've done. So to try to make it clear what we're going to do, let's just explain what is our present strategy. Okay, so how do we do computations at the moment? Well, the first thing that we do is we write the theory, and by this, I really mean the action and things like that. So we write the action in terms of phi, which is the square root of z times the physical field, G and M. Okay, and the reason why I'm saying that the theory is really specified by the action is that as soon as you give me the action, you've specified the path integral, and I can go ahead and calculate whatever correlators I want. So I work out the Feynman rules. Once I've got the Feynman rules, I can now compute any observable I want. So some sort of a correlation function, maybe a cross section, something like that. But we compute observables in terms of Z, M, and G. So we'd go ahead and calculate and get an answer in terms of Z, M, and G. And of course, this answer will depend on epsilon. We'll have to take epsilon to 0. There'll be certain divergences. And it will also depend on certain integrals, which are infinite. So I'm going to say there's a dependence on epsilon and infinities. Once we've done that, we then use the matching conditions. We've called them the matching conditions because this is how we have matched our theory up to nature, but this is also often called the renormalization scheme. Okay, so for your matching conditions, this would also be called some renormalization scheme. And what do the matching conditions do? So use the matching conditions to determine Z, M, and G in terms of the physical mass and the physical coupling. Okay? And then now you've got Z, M, and G in terms of the physical mass and physical coupling. So you can express your observables in terms of the physical mass and the physical coupling. And once you've done that, so your answer that you get has no epsilon dependence. So it's a trivial thing to let epsilon tend to 0, and there's no infinity, so you can go back to 4 dimensions. So, and there's no infinities. So you can easily let epsilon go to 0, which means you remove the regulator. So that's what we've been doing up to now. So renormalized perturbation theory uses what I would say is a more logical approach. Certainly it's more economical, but I think it's more logical. So what do you do in renormalized perturbation theory? So the first step is you write the theory. So again, by this, I mean the action. We really compute everything. Once you're given an action, we're given everything in terms of the physical field, the physical coupling, and the physical mass. But of course, you can't just express the action in terms of those. You also need to add some, and these in general are unknown, and I'm calling them counter terms. Now, I don't expect you to know what a counter term is. So these counter terms that I've just introduced, we're going to define them below. Okay, so just suspend your curiosity. They'll be coming very soon. And in this point of view, the matching conditions determine the counter terms. But you don't need to, start off expressing things in terms of G and M and phi, which are not observables, then figure out how Z, M, and G are related to something that is observable, and then express everything in terms of what's observable. Because we've expressed the theory in terms of the physical field, the physical coupling, and the physical mass, that additional step of re-expressing things is simply not needed. So this is a very economical approach, and there really are just two steps. So let me explain to you now how it works in practice, and let's introduce the counter terms. So let's take as our starting point for the Lagrangian, just 1/2 d mu phi. So this is what we wrote down before, minus 1/2 m squared phi squared. Again, that's our old term, minus g phi to the 4. Again, our old term. Let's just work a little bit below because we'll be writing out what the new Lagrangian is as we develop it. Good. Okay, so let's start off with 1/2 d mu phi. So what is this equal to? Well, remember that phi is equal to the square root of z times by the physical field. So plugging this into that expression, we get 1/2 z d mu phi p d mu phi p. Now this is okay. It is expressed in terms of the physical field, but it's expressed in terms of z. And I'd really rather not have the z dependence. So we can write this as 1/2 d mu physical field, plus, then we'll have 1/2, and now we have delta z, d mu the physical field, d mu the physical field. And delta z that I've just introduced here, this is what we call a counter term. And we can easily work out what the value of the counter term is by comparing the two lines that we've got here. So what would delta z be? Well, this term with the delta z must be equal to the term on the right-hand side, the 1/2 z d mu phi p minus 1/2 d mu phi p. So just by comparing, actually, let's do it in blue. Just by comparing, we know that 1/2 delta z d mu phi physical must be equal to, so 1/2 z d mu phi physical minus 1/2 d mu phi physical. Well, the 1/2 d mu phi physical matches in these terms. The 1/2 matches in these terms. So we learned that delta z has to be equal to z minus 1. Now, whether you want to call z your unknown or delta z your unknown is completely up to you. Our approach is going to be to call delta z the unknown, and we'll be solving for delta z from the matching terms and not z. Okay, good. So the matching conditions before determine z, now the matching conditions will determine delta z. So let's write down our first contribution. So we've got 1/2 d mu phi physical, and then we've got the counter term, 1/2 delta z d mu phi physical, Good. Then we want to add in the mass term. So let's now do something similar for the mass term. So the mass term is minus 1/2 m squared phi squared. So the first thing that we can do, let's express this in terms of the physical field. So it'll be minus 1/2 z m squared phi physical squared. But then I would like to express this as minus 1/2 m physical squared, phi physical squared. That's the term that I would like. But for this to be true, I need to add a counter term. So this will be 1/2 the counter term delta m squared and phi physical squared. And working just like we did before, we can say what the counter term is. So the delta m squared counter term will be mp squared minus zm squared. And once again, I got this just by comparing this line to that line, okay? So that's how I got the mass counter term. So let's add in these two terms. So we'll have minus 1/2 the physical mass squared, the physical field squared, and then we've got the counter term. You know, yeah, good. Plus, let's just see, I didn't make a mess of anything, did I? No, I don't think so. Plus delta m squared over 2 by physical squared. And then we would do exactly the same with the coupling term. So we would have a minus g physical, phi physical to the 4, and we would then need to add in a counter term, minus delta g phi p to the 4. Good. So this is actually what the Lagrangian would be in renormalized perturbation theory. And I have outlined it now in this blue box, okay? And you've seen how to get hold of the counter terms. I didn't write down what the counter term delta G was, but that's a good test to see if you can get hold of the counter term delta G. You should be able to. Okay, let's keep this Lagrangian. I want to discuss it a bit more below. We'll actually use it, so let's rescue it. Good. There we go. Let's duplicate. And let's move this downstairs. So we are going to use this. Oh, what happened? Let's just move that there. We'll do that. And let me just move this up a little bit. Good. Okay, so there's the Lagrangian. Now, so quite clearly, we've got a new Lagrangian. Well, the Feynman rules come from the Lagrangian. So if we've got a new Lagrangian, we'll have a new set of Feynman rules. So what are the new Feynman rules? In particular, by the way, we will have quite a few more Feynman rules than we had, because our new Lagrangian has got 6 terms. Our original Lagrangian only had 3 terms. Okay, so from the first 2 terms over here, by studying those 2 terms, you could work out what the propagator is. And the propagator is equal to I p squared minus mp squared plus I eta, okay? And one thing that you notice about this is that this is written completely in terms of measured quantities. So it's in terms of measured quantities. So what do I mean by that? Well, it only depends on mp squared, and that's what you'd measure. But notice this has the correct residue and pole. So that's nice. It's manifestly got the correct residue and pole. So we must just make sure that whatever corrections we add don't change that. Very good. Okay, we'll continue going in a moment.